Hello friends, welcome to Align Pattern. Today's session is all about how to represent a floating point number to 32-bit IEEE 754 format, or we can say to 16-bit IEEE 754 format. So let's consider our previous example as we have seen in decimal to binary conversion video. If you haven't watched that video, I will provide you the link in the description box. Don't forget to like and subscribe the channel Align Pattern and do motivate me to create more videos. So first, let's consider previous similar example as 53.625 to the base 10. So the first step is that let's convert it into the binary format. We have learned that how to convert decimal to binary format in the easiest way. So I have directly here put it down the conversion answer. Please watch that video for better understanding. So the conversion of 53.625 in binary format is 110101.101 to the base 2. Okay, so let's convert it into the scientific notation. For that we have to shift this point to left side till we reach after one sign bit. So we will be shifting to 1, 2, 3, 4, 5. Okay. For each shift to the left, you need to multiply the number by 2. So we are shifting it to the 5 times to the left. That's why we are writing down 2 raised to the power 5. Okay, got it? So this is the scientific notation, that is 1.10101101 into 2 raised to power 5. So the third step is that we have to write this binary scientific notation format to IEEE 754 format. So if you take a look at IEEE 754 standard format, you would have seen that first bit your 1 sign bit, next 8 bit is your 8 exponential bit, and remaining bit will be 23 bit fraction bit. Okay. So if you consider our number 1.10101101 into 2 raised to power 5, we have a first bit, that is the positive bit. Here is again here is the protocol that if you are having a negative number, the sign bit will be assigned as 1. Otherwise, if it is positive, it will be assigned as 0. So here our number is positive, that is why the sign bit will be assigned as 0. Next, actually the 8 bit of the representation is our exponential bit, that is the exponent of 2 in the scientific notation. So here we again need to consider about bias, as because our exponent number may contain positive or negative numbers, so they have given a certain number as the bias value, and the exponent bias for a single position number is 127. Just remember. Okay, so our exponent bias is 127. So if you have a negative exponent number, you have to subtract the number from bias value, and if you have a positive exponent number, you need to add it. Since this is the positive number, you have to add to the bias value. So our exponent number is 2 raised to power 5. Okay, so that is the positive exponent value, that is 5. So 127 plus 5 is equal to 132 after adding 5 to the bias value. Since 132 is in decimal format, we have to convert it into the binary format. Okay. We already know how to convert decimal number to binary format. If you haven't seen that video, please check in the playlist so you will better understand this concept. Okay, the first step is to divide 132 by 2. Use the integer quotient obtained in this step as the dividend for the next step. Repeat the process until the quotient becomes 0. Okay, so write the remainder from bottom to top. So the binary equivalent of decimal number 132 is 10000100. Got it? So in IEEE 754 format, we got 8-bit exponent as 10000100. Got it? We have a 23 fraction bits, that is the numbers follows by decimal point in the scientific notation. This is also known as the mantissa. Okay. So our third step is that we have to do it's in the normalized form. We have a scientific notation number as 1.10101101 into 2 raised to power 5. Remove the leading, that is the leftmost bit, since it's always 1, and the decimal point if the case. Okay, adjust its length to 32 bit by adding necessary number of zeros to the right. Okay, so our normalized mantissa in this case is this. So the three elements that make up the numbers 32 bit single precision IEEE 754 binary floating point representation is like this, that is a 1 sign bit, 8 exponent bit, and 23 mantissa bit, that is the fraction bits. Okay, Now let's consider the example which we have seen our computer fundamental set for, that is our floating point number 0.15625. So our first step is to convert this into the binary format. Since this is the only fraction part, multiply this by 2. Okay, so 0.15625 into 2 is equal to 0.3125. We got the result 0.3125 after multiplying by 2. So this 0 we have to write it down. Again multiply remaining part by 2, set 0 aside and multiply 0.625 by 2. You will get 1.25. Again set 1 aside, multiply 0.25 by 2, you will get 0.5. Set 0 aside and multiply remaining part by 2 until you get 0 after decimal point. Okay. So we will get 0.15625 into binary format is 0.00101. Got it? So if we write down this number into scientific notation, then we have to shift decimal point to right, so that only one non-zero digit remain to left of to it. Okay, so our number would be 1.01 into 2 raised to power minus 3. Got it? So here our number is positive, that's why our sign bit would be 0. We have got exponent of 2 is negative here. So subtract 3 from 127. So 127 minus 3 is equal to 124. So our exponent bit in this case is 124. Got it? Let's convert 124 to binary format with the same step as we have seen. Okay, so our binary format of decimal number 124 is 111100 to the base 2. Okay, so we have to adjust it up to 8 bits. So by adding 0, our value is 01111100. Got it? So our 8 bit exponent, that is exponent bit, is 01111100. Okay, now consider our mantissa part. Our mantissa is part is 1.01 into 2 raised to power minus 3. So remove leftmost bit since it's always 1 and adjust the length up to 23 bits, as our fraction part is having 23 bits. So we have to add necessary number of 0 to the right. Okay, so our normalized mantissa in this case is this. So by removing this one, our mantissa part is only this 0 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 up to 23 bits. Okay. So the three elements that make up the numbers 32-bit single precision IEEE 754 binary floating point number representation is like this: 1 sign bit, 8 exponent bit and 23 mantissa bit. Okay, I hope you got it. Thank you so much for watching the video. See you on the next lecture.